Now in this session I promised you I would show you the graph of the sine squared term graphed versus the angular frequency omega. So your omega this way, and this vertical axis is your sine squared term. And if you plug in different values of your omega, you assume this is a given, whatever, and with a computer plot you get something like this. Now let's see, why does that make sense? Now we can estimate the value of the peak here. So well, firstly this peak, right, at the value omega when omega equals omega mk, right? It peaks. So that's sort of to be expected. Right? You get a kind of resonant effect, resonating effect. Your AM, if you square it, that gives you a probability of a transition from state, eigenstate UK to UM. Right? So that's not surprising. Now, when omega is very close to omega mk, you can estimate what this is. Remember, I suppose you did it in calculus. If x is small, very small, then sine x is almost equal to x. Right? So you can approximate sine of x as just x when x is very small. So can you see that? So let this be x. So omega mk minus omega. Let that be x, and x is small. So you've got sine squared of a half xt. So when x is very small, that's roughly the square of a half xt. Make sense? And this is just x squared. So you've got a half, the x's cancel, so you've got a half t squared, which is t squared over 4. Alright? So this height here is just t squared over 4. So now if you think about that, the longer your t is in your integral for a1, your am1, the first order correction, the longer that time interval is, t, the larger this is going to be, right? And it's t squared, so it'll go up very sharply. So you'll get quite a strong resonant effect, okay, over a long t, as t is large. This distance here becomes large, is the square of t. Alright, now what about the width here? Well, let's see, why does this function become 0 at these terms? Does it make sense? Yes, it does. Plug that value into here, the omega mk's cancel, you're left then with 2 pi over t times t, which is 2 pi, and sine of a half of 2 pi, sine of pi is 0. Okay, does that make sense? Similar logic for here. So so this term becomes 0 at here and these two values. So that allows you to calculate roughly the width of this peak. So it'll just be the difference between this value and this one, which is 4 pi over t. Okay. So so knowing we have an estimate of the height, that's t squared over 4. The width is 4 pi over t. So that means it's common sense. The longer the time interval that you're integrating over, from 0 to t, as that t time period, as it gets larger and larger, the probability of a transition, which involves this, goes up, right? A lot. It depends on t squared. And the width here, or if you like the narrowness, as t gets larger, well, this width here gets narrower and narrower, depending on t. Okay, so it really is. It becomes quite a sharp peak. But this is not a delta function, as I was saying in the earlier session. Right? The width is proportional to 1 over t. Now that's interesting. Now what does that mean? Now I'll come back to this in the next square as we start. As usual, I run out of board. Well, I'll mention it a bit now, what's coming. There's a form of the HUP, HUP, Heisenberg uncertainty principle. Now you're most familiar with the HUP in terms of delta x delta p, right? The delta meaning uncertainty in, defined as a standard deviation, if you like. So delta x delta p, uncertainty in the measurement of the position times the uncertainty in the measurement of the momentum is of the order about h bar over 2, I think. So we did that. And when we did in general, for any two incompatible observables, A and B, incompatible meaning you can't measure both of them at the same time to infinite accuracy. Right? They're incompatible in that sense. Then we derived an expression that was also a product of two standard deviations. Okay, so that's the usual one you're used to, but we're heading now towards an alternative form in terms of E, the energy, and time. So there'll be something like delta E times delta T, also proportional to h bar, this kind of thing. So the delta E is the uncertainty in the energy measurement, and the delta T is the uncertainty in, I'm not quite sure, the time of what? I need to think a bit about that. I need to give that a bit more thought. What does the delta T actually refer to? So this alternative way of looking on the Heisenberg uncertainty principle is, delta E times delta T is of the order h bar. And what is delta T? Now I'll come back to that in a later session. All right. Okay. So in this sense, you've got a kind of resonance occurring, and what's happening? So when your omega is almost omega mk, so h bar omega is almost h bar omega mk. This, by definition, your omega mk is 1 over h bar times the energy difference. Okay. So if so we interpret this to mean that when your t is fairly large, so it's a slow transition, but your AM goes large, with a long t squared is very large, so you get this very thin. The width is of order 1 over t, the height is of the order t squared. So you get a strong probability. Your AM will be large, right? Strong probability that it'll switch. And physically, how do you interpret that? What's happening? Well, your energy levels are going to switch. Okay, so for example, you're talking about quantum system, say an atom, then you're transitioning, you're changing state from say UK to UN, and that's assuming this omega is positive, so this will be larger than this. So you're exciting the atom. Electron will move up from a lower energy to a higher energy, an excited energy. Okay? And the difference between these two energies will be equal to this, which is equal to that, more or less. Right? So what happens to the difference in the energies? Okay? So in classical mechanics, conservation, the law of conservation of energy is basic. So what's happened to the difference. Now this is the difference in the energy of your quantum system, so an atom, so the electron. So if it's now excited to a higher energy level, where did that energy come from? So before the transition, it was at a lower energy Ek, and now it's at a higher energy Em. So where did that energy come from? Well, from the perturber, the electromagnetic field, let's say, that's perturbing the atom. So probably that would mean, now if you quantize an electric field, and that's the whole point of quantum field theory, but that's master's level. When you quantize an electric field, they are photons, right? The photons are quantized electromagnetic fields, in effect. So what's happening, in fact, to get this increase in energy from lower state to higher state energy, a photon comes in and perturbs the electron, which bumps it up to get a quantum jump, in effect. Well, that was something that Schrödinger believed in. Bohr was very skeptical and pummeled him. Remember, I talked about this at one stage. Poor old Schrödinger got fresh off the train from Wien in German, to Copenhagen, and was pummeled with questions by Bohr. Bohr did not like the idea of quantum jumps. He thought that was sort of meaningless. Anyway, so do you talk in terms of quantum jumps or not? Interpretation of quantum mechanics, very hot. Hot in the sense, not just popular, but, well, it was not very popular. It's only fairly recent, last decade or two, that it's heated up in that sense again. But hot in the sense of controversial, right? The people's quantum mechanics, the people who do quantum mechanics, get hot under the collar. They get, their temperature rises when they talk about interpretation of quantum mechanics. Because there's so much that's at stake, right? Quantum mechanics describes the world, our universe, so intellectually it's of huge importance, and it's not understood. This interpretation of quantum mechanics is highly controversial, and who knows, maybe a century from now Einstein may have ended up to being right, but who knows, maybe not. Okay. So this difference in the energies is due to, for example, absorption of a photon. So that